Okay, now to the last two parts of this class. One is hypothesis testing to compare means. So you might have two groups. Let's say the women who die during labor. You want to see if the age of those women who died during labor was any different from those women which survived labor. So you would get a mean age of women who survived and the mean age of the women who died. And you would want to compare these means. So this is just one example, but this is what hypothesis testing, when we are comparing means, is all about. Let's go further in that. So you might be required to compare means in several different situations. Let's see those situations one by one. You have a one group, you have an entire group, and you have one single mean value. And you want to compare this mean value with any reference value that is available in literature. This could be one problem. Or you might have two values in which you are required to compare two means from paired data. That means you've got two groups which are kind of paired or matched to each other, and you want to compare two means. Or you might have a comparison of two means from two unpaired groups. These groups are not related to each other. We'll see a little more examples of these to make it more clearer. But for the moment, let's proceed ahead. And there might be problems and areas when these assumptions which we are making for hypothesis testing are themselves not valid. Then what to do? And there might be situations when you might be comparing means between more than two groups. You could have 3, 4, 5, 6 groups. Let's say we might ask women what is their favorite color, and we want to compare the ages of women who liked blue, compare it with those who liked red, compare it with those who liked yellow, compare it with those who liked green. So we might have more than one group and we want to make those comparisons. So when we have to compare one observed mean with a reference value, what we use is one sample test. So yes, we will talk about how to clinically correlate all these. We will do that in the next slide. We might be requiring to compare means between two paired data. Then we would use a paired t-test. So it's always a t-test when you're comparing means. It is a one sample t-test. This is a paired t-test. When you're doing it between two groups which are completely different, then it's an unpaired t-test. When your sample size is very small and you have very few patients, then what you use is non-parametric tests. And when you want to compare means in more than two groups, then you use ANOVA, which we talked about a little while earlier, which is the analysis of variance. Now let's look at each of them with examples. So which test would you use if, let's say, you wanted to look at the hemoglobin levels of all women coming from village Balongi, and you wanted to see if this hemoglobin level is not different from the average hemoglobin in the state of Punjab? Which test would you use? Grishmika says paired t-test. So where is the pair? We have only one group of women who are coming from village Balongi. We don't have anyone else. We just have in literature the average hemoglobin in the state of Punjab, but we are trying to find if this group from Balongi matches with the state of Punjab, or is there a disease in these women from Balongi? Is there an endemic that is happening in Balongi and they might have less hemoglobin? Yes, Ananya says one sample t-test. Sonal says one sample t-test. Yes, Shruti, it's always t-test. Aditi, it's always t-test. But we are looking for a one sample t-test because we have only one sample. We have only those women who are coming from village Balongi. Let's go ahead. Let's look at the next one. And we have, we're trying to look at hemoglobin at the time of ANC at 6 months. So all the women who are 6 months ANC, and I believe that this is not going to be different from the hemoglobin in the same woman after delivery. So what kind of a test will we use in this? So we have one value of hemoglobin of the woman or the mother at 6 months, and we have another value of hemoglobin after her delivery. The paired t-test, because this is samples from the same woman who was at 6 months and after delivery, and we find that these are paired samples of these individuals. That's a paired t-test. In the next example, let's say there are we are looking for hemoglobin in mothers who have ANC at 8 months, and we want to compare whether this is not very different among women who are coming from Haryana. So we have two groups. One group is from Punjab and one group is from Haryana. And we have matched their age, sex, socioeconomic status, and also parity. So we have matched these women from Punjab and Haryana on age, sex, socioeconomic status, and parity. Now, can you tell me whether you will use paired test or unpaired t-test? So the key thing to remember here is that these women who are coming from Punjab had been matched. They are matched. They've been matched on at least 4 parameters. And because we matched, we have to use the paired t-test. If we had not matched them, then we would use the unpaired t-test. I hope I have made myself clear in this. So there are two instances when we are using the paired t-test. One, when we have two samples from the same patient, which we want to compare, or we have two different patients and they are matched to each other. Let's see if we were trying to figure out what is the difference between hemoglobin of mothers who are delivering in December, and it's not different from the hemoglobin of mothers who are delivering in May. I want to compare. Now, I can give any kind of research question, however absurd it might sound, but to make it simple, I want to compare the hemoglobin of all mothers who deliver in December and compare it with the mothers who deliver in May. If there is any difference between the time, which kind of test would we use? Yeah, this time you're correct. Everyone says unpaired t-test. Absolutely, we are going to use unpaired t-test because there is no relation whatsoever between those mothers which delivered in December and those which delivered in May. Now, supposing we were trying to figure out the weight of patients with CA cervix, and I believe that this is not different from age and socioeconomic status matched women without cancer cervix. So which test do you think we will use here? And I'm sure all of you will get the answer right because the keyword here is matching. And just like the previous example, when they had been matched, we will be using the paired t-test because of the matching that we had applied. There are certain assumptions that are made for the t-test. Let's look at them. So when we are using the one sample t-test, we believe that the distribution of this sample is normal. And unless this assumption is true, then our test becomes invalid. When we are using paired t-test, we believe that the differences are distributed normally, that the differences are distributed normally. That is what we assume. And similarly, when we use the unpaired t-test, then we believe that both the groups are distributed normally. And in addition, both the groups have an equal standard deviation. So Aditi wants me to display the previous slide. Is that what you want? Is this the example slide that you wanted me to display? So I think that was what she wanted. Fair enough. So if there is a modest departure from these assumptions, supposing a data is slightly not normal, or the slightly different standard deviations, then the t-test still holds. There is no problem. We can continue with whatever we were doing. T-test is valid. However, if there was major departure, then we either transform the data or we use non-parametric tests. Let's look at what are non-parametric tests. So what are parametric tests first? What is the meaning of this word parametric? So when we say parametric, it just means that it requires the determination of some parameters to satisfy normality. And what are these parameters? The median and standard deviation. So that's why they're just called parametric tests. Now, non-parametric tests do not require any parameters, and they have slightly lesser assumptions, which are less rigid than the parametric tests. Now, if we are using the one sample or the paired values, like we did in the previous example, then the non-parametric test to use will be sign test or the Wilcoxon signed rank test. Now, I'm not going to go into the detail of each of these tests. My intention is not to teach you how to do these tests. Obviously, any software in 2022 can do it. And like we saw, we just need to go into the pull down menu. It will drop down box and it will show us, it will just give us that test. We feed in which variables we want to do, and it will do it for us. So if we have two unpaired samples, we use Wilcoxon rank sum test, which is also called the Mann-Whitney U test. So when you have non-parametric tests to use, one sample, or if you have paired values, you use either of sign test or Wilcoxon signed rank test. And if you have two unpaired samples, you use a Wilcoxon rank sum test. We will look at this more in the last few slides. So the non-parametric tests have some advantages. They are preferable when the data is not normal, when you have a small sample size, when you have some unexpected values, or there are very many outlying observations, very big or very small observations, or they are intuitive, they are simple to compute, and they are useful for ordinal data. So you remember what was ordinal data? When there is an order in the data, mild, moderate, severe. So ordinal, please remember the word ordinal is order. So when there is a natural order, low, high, medium, fat, thin. So that kind of an order, when it is there, then we say it's ordinal data. So that's when we use the non-parametric tests. Obviously, if they have some advantages, they will also have some disadvantages. They lack power as compared to the traditional tests, and they're geared to hypothesis testing. They will not tell you whether the effect is small, large, strong, mild, but they will just tell you whether it is significant or not significant, is the hypothesis standing or not standing. And it's difficult to get confidence intervals in cases of non-parametric tests. But anyway, any software can do it for us now. So let's do a quick display and demo on t-test and Wilcoxon ranks test. So let's go back to our demo version. And I want to see if the age of the women were different from age of the men. So let's try and see what is the difference, if there is any significant difference between the mean age of men and women. So I don't want you to remember the formulae, but let's say I'm doing it by showing you the drop-down boxes, because so that if any one of you wants to buy or use data, then it will be easier. It's not very difficult. Go to summaries and tables. We go into classical tests of hypothesis. So remember, we are working on the classical tests of hypothesis, and we are trying to see the t-test, which is the mean comparison test. Now, we were using two sample using groups. So we are going to use two groups. The groups are divided by sex, male and female, and the variable is age. So what we wanted to do was see whether the age is difference between the males and the females. And we just click submit. and we get it in the background in the results window. It tells us that the mean of men, which were called 0, is 51 years, and the mean of women, which were called 1, is 53 years. So if you see broadly, there is a difference of 2 years, 2.5 years between the men and the women. There were 36 men and 34 women. Now, if we look at the standard deviation, it gives us the standard deviation, it gives us the mean. And if I look at the confidence intervals, I see that the confidence interval is from 45 to 56 in case of men, and 46 to 60 in case of women. So you see there is a huge overlap. So it could be anywhere in between, right? So obviously this cannot be significant. If we look at confidence intervals, that gives us that broad range from 45 to 56 and 46 to 60. And that is why we say that the overlapping confidence intervals indicate that there is no real difference between the men and women ages. And similarly, if you look at the p-value here, this where my cursor is pointing is the p-value, and the p-value is 0.55. Obviously, it is more than 0.05, which are our significance level. So it also indicates that there was no real difference between men and women in this age group. So let's say if we were using one of the non-parametric tests, what would happen? Let's do the same exercise with a non-parametric test. And here are the non-parametric analysis. Okay, yeah, statistics, non-parametric tests. And these are the tests of hypothesis. And we said we will be using the Wilcoxon rank sum test to differentiate between the two groups. Again, our age is the variable that we are trying, and the grouping variable is sex. So when we do submit, it gives us the result in the background, and we find that it gives us several things, and the probability p-value is this one, which gives it here, which is 0.5. And again, it has calculated a rank sum. We never report any of these. So when you're writing a paper, you don't report any of this jargon, which is here. You only want to tell that the probability was 0.5 and it was not significant. And when I use the Wilcoxon rank sum test or the Mann-Whitney U test, I found that the age was not significantly different between the men and the women. So that's so much for the demo. If there are any questions, we will address them here.